Hello and welcome back to my channel. Students, in this problem series, as we know, we are doing organic chemistry through problems. And in this course, currently we are focusing on stereoisomerism. So straight away, let us see question number 33. Now, as you see the question number 33 on your screen, you find that there is a three-dimensional arrangement of a compound X given on your screen. The compound X is portrayed on the basis of sawhorse projection. So there is a complete three-dimensional diagram based on sawhorse projection, and based on this three-dimensional projection formula, you have to answer amongst these A, B, C and D, which is or are the correct options. Now, first of all, let us try to understand this sawhorse projection formula. What does it speaks about? And also in the course of time, we will calculate the number of chiral carbons. We will see whether as a whole the compound is chiral or not. And also we are going to convert this sawhorse projection formula into Fisher's projection. And therefore, we will carry on with our options. Now, coming on to the three-dimensional formula, as you can see on your screen, the sawhorse projection. If you try to watch for the chiral center, then the first carbon you encounter in front of you, you find that this particular carbon is attached with four different groups: hydrogen, methyl, chlorine, and the fourth group, as you can see, is completely different. So all four groups are different. So this particular carbon is a chiral carbon. Now, moving one step further, you understand this carbon. Now, if you see this carbon, you find that this is not a chiral center. Why this is not a chiral center? Because two groups are same. As you can understand, with this carbon, two groups are hydrogen, and for chirality of a carbon, you can't have two groups or more as same. All the four groups must be different for the chirality of the carbon. So this is not a chiral center. Now, moving one position ahead, if you try to investigate about this particular carbon, again you find that this is a chiral carbon. Why? Because again you find four different groups: hydrogen, this whole group, methyl, and this group. So all the four groups attached with this carbon are different. Therefore, again it's a chiral carbon. Now, moving one position ahead, if you try to investigate about this particular carbon, you find that again it is a chiral carbon. Why? Because four groups are different: hydrogen, methyl, chlorine, and this front group, as you can understand, is different from the other three. So from this particular very simple investigation, we have found that it carries three chiral carbons. Now it is our duty, it is now our turn to convert this sawhorse projection formula into Fisher's projection formula. So earlier what we have seen is sawhorse projection formula. Now we will convert this sawhorse projection formula into Fisher's projection formula. Now, to do that, let us try to see a few very simple basic steps which could convert this sawhorse formula into the Fisher's projection formula. For that, let me make the screen clear. So now what you have to see is, you understand, since there are three chiral center, 1, 2 and 3, so in the Fisher's projection formula you should have three intersections of horizontal and vertical line which will represent the three chiral centers. Now, how to put the groups in the Fisher projection formula, let us try to understand. If you watch this formula from this side, now you watch for the formula, source formula in this direction, you put your eyes here and you watch for the formula, you will find that the methyl and chlorine are coming out of the plane of paper. It is coming towards the eyes and hydrogen is going away. So you understand, in the Fisher's projection formula, I have taken this chiral carbon as this carbon, where if you try to see in front of this, from front of this formula, you will see that methyl and chlorine will appear to come outside the plane of paper and towards your eyes, and that is what you have portrayed, the methyl and chlorine coming out of the plane of paper, and the groups coming out of the plane of the paper must be on the horizontal line. And hydrogen, you understand from the Fisher projection formula, it is going inside the plane of paper, or you can say away from you. So this is a correct representation. Now coming to the next carbon, again you can't picturize it as the intersection of two lines. Why? Because it's not a chiral carbon, so I have written it as simple CH2. Now progressing one step ahead, this particular carbon I have represented it like this. Again, if you try to see these two chiral centers, you do one thing, you just rotate this last carbon by 60° in the clockwise direction. Once you do that, you will find that these two hydrogen come same side and these two methyl come same side. So if you try to put your eyes in this direction and see, then you will find that the two methyl and the two hydrogens are coming towards your eyes. And so if you try to see the two chiral centers I have drawn, the two methyls and two hydrogens are on the same side first of all, and they are on the horizontal line. It means that they are coming towards the observer, and that has to happen if these are to be on the horizontal line. So from all these basic fundamentals, we have converted the sawhorse projection into a Fisher's projection formula. Now if you try to see this Fisher's projection formula, so I have taken the new slide. In this new slide, I have basically taken the compound X, and the projection I have given is the Fisher's projection. And if you try to take a mirror image of this compound X by putting a mirror, I have drawn the mirror image also, and if you try to compare these two mirror images, you will immediately recognize, you will immediately find that these two are non-superimposable mirror images. These two are non-superimposable mirror images. It means these two are enantiomers of each other. These two are separate isomers which are called as enantiomers or optical isomers, and both are optically active. If for an example you take X and suppose it rotates the plane polarized light in the clockwise direction, so the mirror image will rotate the plane polarized light in anti-clockwise direction. So from this particular action of letting us know that the two are non-superimposable mirror images, we can take out certain inferences, like first of all, this compound has got three chiral centers. Second, the mirror images are non-superimposable. Third, since the two are non-superimposable, so the compound X must be optically active, and it may, you understand, for you understand, rotation of a plane polarized light, you have to detect it experimentally. It may rotate in clockwise direction or it may rotate it in anti-clockwise direction. Any one direction will operate, either clockwise or anti-clockwise. So now if you try to see the options, first option, it may turn, look at the word may, it may turn the plane polarized light in the clockwise direction. So it has not said it must, since it is just showing a possibility that it may turn the plane polarized light in clockwise direction. So it's a correct possibility, and you must go with this option, because it is trying to say that first of all it is optically active, and since it's an optically active compound, it will definitely have action towards plane polarized light, which may turn clockwise direction or may turn anti-clockwise. So from this logical approach, you can say that the option A is correct. Now coming on to the option number B, it has a plane of symmetry. Now you should understand, if this compound had plane of symmetry, then the two mirror images you have drawn, must be overlapping on each other, must be superimposing on each other, because if you have plane of symmetry in a compound, that compound must be optically inactive, and if it is optically inactive, it will definitely superimpose on its mirror image. And since you have known by drawing the two figures that these two are non-superimposable, so this compound X cannot have the plane of symmetry, because the presence of plane of symmetry simply indicates that it is optically inactive, and if you are going to draw its mirror image, both are going to superimpose on each other. Since it is not happening, so if you come to this option, it has a plane of symmetry, this option goes wrong. Now coming on to the option number C, it has 6 diastereomers. So now you must understand what is the meaning of diastereomers, and I will draw all the isomers first of all, and then will describe what is the meaning of diastereomers, and then finally calculate the number of diastereomers. For that to happen, I have drawn all the possible, you understand, this compound has got 3 chiral, the structural formula, if you see, it has 3 chiral centers. And if it has 3 chiral centers, you understand, the maximum number of stereoisomers it can give is 2 power n, where n is the number of chiral centers, and since it has 3, so it gives 2 power 3, that is 8. So maximum it can have 8 number of stereoisomers, and I must tell you it will have 8 stereoisomers, because this compound, this structural formula in any 3-dimensional configuration lacks plane of symmetry, it lacks center of symmetry, it lacks alternate axis of rotation. I mean, what we understand that there is no symmetry which could decrease the number of stereoisomers from 8 to a lower value. There is no such symmetry present in any of the structure you can understand. So you will get definitely 8 maximum number of stereoisomers in this case. And all the 8 I have drawn, you understand, the 8 you have drawn basically will come in 4 pairs. So you will have 4 pairs of enantiomers. So very importantly, you should understand, since there is no mesophore and all the 8 are optically active, it must happen that they must come in the pair of enantiomers, and by that there will be 4 pairs of enantiomers. So if I take this as my argument, then the last option, if you see, the given structural formula gives rise to 3 pair of enantiomers, is wrong, because it gives rise to rather 4 pairs of enantiomer. Now again the option C is open for us. Let us try to see what is the meaning of diastereomers, and then shall calculate the number of diastereomers. Now you should understand what is the meaning of diastereomer. Diastereomers are those stereoisomers which are non-mirror image of each other. They should not be mirror images of each other. So for an example, if I am trying to say that calculate the number of diastereomers of X, so you will find all those stereoisomers which are not the mirror image of X first of all. So you will not calculate this, because this is the mirror image and must be stereoisomer of X. So if you leave this, the number of diastereomers then will be 1, 2, 3, 4, 5 and 6, because all these 6 are neither the mirror image of X and also at the same time they are stereoisomers. So diastereomers are basically those stereoisomers which are not the mirror image of given configuration. So from this argument we come to a conclusion that the X has 6 number of diastereomers. So if we come to our original question, so the option C is the correct answer. So you understand, in this question we have two correct options, option A and option C. So if you try to see the complete question, it comes with the very fundamental knowledge of chiral carbons, conversion of Sawhorse projection into Fisher's projection, and then what is the meaning of the term diastereomers, and all these basic fundamentals I have tried to involve in this very important problem. I hope you all must have got the basic fundamentals, basic idea behind this question, because it is all about the concepts. You can solve any question. So I will keep trying to bring the problems like these in future also. Until then, keep watching my videos and take a good care of your health and happiness. Thank you very much.